Okay, so yeah, just a second. Yeah. Okay, so in this sessions, what I will be talking is related to the next topics which we have already seen last class. Last class we talked about Lagrangian and then Hamiltonian and some things related to special theory of relativity, right? So in this sections we will be talking more towards quantum mechanics. That means we are going to try to go towards quantum mechanics. So but before we go to quantum mechanics, okay, we will see why quantum mechanics comes into the picture, okay, and also then we will solve the problems, okay, according to the assignment. We will solve all five of them, okay, and then before solving the problems also I will tell you, okay, what are the formulas that is required. Okay, so similar to the last class I will be following in the same manner. Okay, so if you have noticed the assignments, okay, there are few questions uh, related to your uh, photoelectric effect, and there are also questions related to your Compton effect, and also something related to atomic spectra. Okay, so let's start. Okay, so let's start. What I will be talking first was, yeah. So, what I will be talking, let me just, what I will be talking in this sessions is related to your second, your week two, which is related to your introduction to quantum mechanics, okay, which is related to your photoelectric effect, Compton effect, atomic spectra, okay. Then I think next week will be more related towards um, postulates of quantum mechanics and so on. So in these sections what we will be doing is we'll be doing just the introduction of your quantum mechanics, okay, and then we will solve all the problems related to your assignments, okay. And if you need any more, if you want to solve more problems, okay, you can just inform me, okay, I will prepare the set of questions and then we can also solve those things, okay. You can always inform me, then we can solve some more problems according to your convenience, okay. So uh, yeah, okay. So now, uh, if you want to follow these sections, okay, these sections of this lecture, I have taken most of, you can say the notes or the lectures is from these two books, okay, Quantum Mechanics, Quantum Mechanics, uh, Concept and Applications by, okay, ZB, ZETTILI. Okay, this is available online in PDF format, okay, you can easily access. So this is one of the standard books that, okay, most people follow, okay. It's a very nice books, okay. It contains all the details of the introduction to quantum mechanics and so on. The other textbooks that which I usually follow is Concept of Modern Physics by Arthur Beezer. Okay, these are the two books which I usually follow, okay, especially from the quantum mechanics point of view. ZD is one of the good books, and and in terms of more like general like modern physics, many different topics, then this Concept of Modern Physics by Arthur Beezer is one of a good uh, one of the good textbooks, okay. So okay, let's go ahead, okay, then we can solve problems, okay. So what is the difference between classical physics and quantum mechanics, okay. So from classical physics, whatever you have been talking before, okay, whatever you have known, if I say that, okay, a particle, how do we describe a particle, okay, usually a particle is characterized by an energy E and a momentum P, okay. Suppose if I say that, okay, let's consider a particle, then how do you characterize the particle? So usually you describe what is the energy of a particle, and also you describe another what is the momentum of a particle. That is one point. Second point, suppose you have a wave, okay, any wave. So how do you describe a wave? A wave is characterized by, you know, an amplitude and a wave vector. And a wave vector, let's say k vector, which is equal to 2 pi by lambda. Okay. So according to classical physics, you know, a particle remains as a particle and a wave remains a wave. They are two mutually exclusive. That means they are independent of one another. But is it true? Okay, if we go to quantum mechanics, is it true or not? Okay, according to classical physics, a particle is usually described by an energy E and a momentum P, and usually a wave is described by simply an amplitude as well as a wave vector. That means if I want to highlight it here, this is the amplitude and this is the wave vector, this is the energy, and this is the momentum P. Okay, so what are few sections, or not a few, I will say few experiments that in which classical physics cannot explain, or in which these assumptions cannot explain? Okay, so if you go to your your quantum mechanics, whatever the books I have suggested to you, they have described 3 to 4 phenomena in which, you know, classical cannot explain by assuming this a wave is a wave or a particle is a particle. Okay, so now I will discuss 2 of them. Okay, because this is what also your assignments is related to, questions related to those, but there are 3 more in which you can look upon your textbook. Okay, in which you can look upon in the books which I have suggested you. The first one is, sorry, the first one is photoelectric effect. Photoelectric effect. Second one is Compton effect. Okay, these I will discuss here. And other parts are black body radiation, and so on. Okay, so we will start first with photoelectric effect. I will discuss 2 of them, photoelectric effect. Okay, so what is really a photoelectric effect? You know, so photoelectric effect, simply as simple idea is that, you know, you have, let's say you have let's say a sample here or a metals. Okay, and you shine incident light of energy h mu. Then what happens is going out. Okay, this is ejected electrons. Electrons are, sorry, electrons ejected. Okay, so which has a certain kinetic energy. So that means, let's say you have a metal. Okay, you have a certain metal, and then you shine light, incident light of energy h mu, and then what will happen is that there will be electrons ejected. Now classically, what is classically said? Okay, so classically says that just a second. Yeah, so before we move to classically, what are the observations? Before we move to classically, I'll explain you what are the observations. Okay, what are the observations? So when you do this experiment, let's say you shine light on a metal and then let the electrons ejected, okay, after a certain energy. So what happens, okay, if the frequency mu of incident radiation or incident light, if mu, that means if the frequency of the incident radiation is less than metal threshold frequency, then no electrons are ejected. What does it mean? It means that suppose if your frequency of the incident radiation is less than a certain value, that certain value is called as a threshold frequency, which is depends upon your different materials to different materials. Then if it is less, then no electrons will be ejected. That means electrons will not be able to eject. Second observations. No matter or whatever, no matter how low the intensity of the incident radiation, no matter how low the intensity of the radiation, electrons will be ejected, okay, the moment mu is greater than mu naught. Mu naught here is a threshold frequency. Okay, that means it does not depend upon your upon the intensity of the incident. It depends only on your frequency. If frequency is, point number A is that if it is less than the threshold frequency, no electrons will be ejected. Second is that as soon as your frequency is greater than the threshold frequency, your electron will be ejected no matter what is the intensity. Okay, the third one, which is also important, that is the number of ejected electrons depends on the intensity, but not frequency. Okay, so if I give you the story, that means that if you shine a light on an incident material, if the frequency of the light is less than the threshold frequency, electron will not be able to eject it from the material. But as soon as it is higher than the threshold frequency, then electron will start eject. Okay, and the number of ejected electrons will be proportional to the intensity of your incident light, but not on the frequency. The last one is that kinetic energy, that means h mu is equal to work function of the metal plus the kinetic energy. That means if you want to find out the kinetic energy of the ejected electron, will be incident light minus the work function phi. Okay, so this is the experimental observations. Okay, so why what happens then? Why not classically cannot explain this? Okay, why? So according to classical physics, what happens according to classical physics? Let's say you have an energy h mu. Okay, according to classical physics, you have an energy, not say h mu. Let's say you have a light. Okay, a light source shining on the metal or on the materials. What will happen is that an electron would absorb the energy. Okay, that means as soon as you shine a light on your material, an electron will absorb the energy until it gain a sufficient amount, then it would leave the metals. Okay, but is it true an electron will absorb the energy until it gains a sufficient amount, then it will leave the metals? But that means, let's say if your energy is less and you keep shining it for 1 day, then after 1 day, let's say the electron will get sufficient amount of energy, then after 1 day your electrons will be ejected. But observation is not so, right? Observation says that as soon as you shine light, and if it is greater than the threshold frequency, then instantaneously your electron will be ejected. It does not depend on 1 day, 2 days, 3 days. It does not depend. As soon as if your light is greater than threshold frequency, then your electrons will be ejected. Okay, but here it says that classical physics, as long as classical physics, which means that your electron will keep on absorbing energy until it gains a sufficient amount of energy, then it will leave the metal, which is not true, which is not able to explain, because according to classical physics, then it will take time for the electrons to get a huge amount of energy, then it will eject it. So this is where your classical physics cannot explain. Okay, cannot explain. Now I'll cut short of it. Then what happens to quantum physics? Okay, according to Planck's, he considered energy as a particle. This is where quantum mechanics comes. He doesn't consider energy as a wave, but he considers energy as a particle, given by the energy is equal to h mu, or photons, energy of a photons. Right? According to Planck's, I can say quantization. Okay, what happens is that light, or whatever you can consider as energy, light, whatever light of energy E is considered as a photon of energy h mu. Now what happens if this mu here, if mu or if h mu is greater than h mu naught, right, which is the threshold frequency, automatically your electrons will be ejected. Right? It does not depend on your time, where it requires a sufficient amount of time for the electrons to be ejected out. No, as soon as your h mu is greater than h mu naught, electrons will be ejected. This is where quantum physics comes into the picture, because why? You consider now each energy is considered as a photons, or an energy is considered as a stream of photons of energy h mu. Okay, so that is why your h mu, your particle consideration of photons is becoming into the picture. Now what happens is that now it comes a formula. What happens? H mu is equal to what? H mu is equal to phi, the work function of the metal, plus kinetic energy, right? Or kinetic energy is equal to h mu minus the work function, or work function is in fact h mu naught, h mu minus of mu naught. See, now see this problem. If mu is less than mu naught, mu is the frequency of your incident light, and mu naught is your threshold frequency, then what happens? Kinetic energy is negative, which is not possible, right? So that means if mu is greater than, if mu is less than mu naught, then no electrons will be ejected, right? But classical physics says that, okay, if you shine the light for a long time, then electrons will be ejected. No, quantum physics says that no, not possible. No matter how long you shine, if mu is less than mu naught, no electrons will be ejected. But if mu is greater than mu naught, then your kinetic energy is positive. Okay, so this is one of the formula which is important for you, okay, in any problems. Okay, this is h mu is equal to the work function plus the kinetic energy, provided your mu is greater than mu naught, then your kinetic energy is positive, which means that electron will be ejected from the metal. But if however mu is less than mu naught, then the kinetic energy is negative, which means that electron will not be able to eject, or electron will not able to come out of the metals. Okay, so this is a short a short idea of photoelectric effect. Okay, so there is more details. I will give you the notes also. There is more details from those two books also, in much more detail. Okay, now we'll see now the second problems, which is what is the Compton effect. Okay. Yeah, what is a Compton effect? So now we are talking the next case, which is this one. Okay, so you have, let's say you have an electron, and there is an incident photon on the left. And this incident photon, as soon as your photon hit your electron, what will happen? Electron will recoil. This is called as your recoiling electron. and in this side is called as a scattered photon, okay, at an angle theta. Okay, so here also let's do the same logic. Okay, let's try to understand what happens. Okay, so suppose you have an incident photon of wavelength lambda. Okay, your scattered photon will be lambda prime. Okay, so what is the observation of this experiment? Okay, what is the observation of this experiment? The observation says that, you know, there is a difference between your scattered photon and your incident photon. That means there is a change of the wavelength of your incident photon and the scattered photon. That means there is something like del lambda is equal to lambda prime minus of lambda, or lambda prime is not equal to lambda. Why? I mean, this is the experiment which they found out. That means your scattered photon is not of the same wavelength as your incident photon. They are the same photon, right? But they have a different wavelength. So, but classically, what happens is uh, classically, so this is the observation. That means your scattered photon is not of the same wavelength of the incident photon. So classically, or classical from classical physics point of view, in which we consider, just let's say that energy as simply a wave, okay, which is not in terms of a quantized h mu. What happens is that classically, since energy of x-ray, okay, let's consider this as an x-ray or incident photon, x-ray radiation is too high to be absorbed by an electron, the incident X-ray will then provide an oscillatory electric field, okay, which sets the electron into oscillatory motion. Okay, then what happens? What happens because of your now the oscillatory motion? What happens is that making it radiate. Sorry, I will write here. Hence, making it radiate light with same wavelength, okay, that depends on the incident radiation ion. What classically says that? Classically says that, you know, when you pass an incident radiation, or in this form, or could be an X-ray, when you say an X-ray to an electron, what happens? Your electron will undergo oscillatory motion. So when it undergo oscillatory motion, what happens is that it will generate again radiation with the same wavelength, and the intensity, okay, and the intensity depends upon the incident, and the intensity of the radiated light will depends upon the intensity of the incident radiation I naught. Okay, but observation says that lambda prime is not equal to lambda, is it? Lambda prime is not equal to lambda, but classically says that lambda prime should be equal to lambda. That is where here again we have to consider from quantum. We don't consider the incident light as a continuous energy, right? We consider a light as h mu. Right? Now what happens is that I will show you a short steps. Okay, if you solve these problems, okay, using conservation of energy, okay, what will happen is that let me just rewrite here. Incident photon, let's say it has a momentum p and it has an energy E, which is equal to h mu. Okay, the final momentum will be equal to p prime and also energy E prime is equal to h mu prime. Scattered for recoiling electron will be energy of the electron plus the momentum of the electron. So what happens is that if you solve conservation of energy, that means the total momentum, the total initial momentum P of the incident photon is equal to the momentum of the electron, that is the recoil electron, plus the scattered photon P prime. Okay, so this is equation 1. The next one is the energy. So this is sorry, this is not conservation of energy, this is conservation of momentum. Okay, and the second one is the conservation of energy. Conservation of energy, that means E, which is the energy of your incident photon, plus E naught. E naught is what? Is the energy of the electron at rest, right? Because the electron, because your incident photon of energy E, this is electron of energy E naught, right? It should be equal to E prime plus the energy of the electron, right? So this is the energy of your incident light. This is the energy of the electron. This is your scattered photon or scattered light, I can say. And this is your recoil electron. Okay. So if you solve this equation together, I will not solve. This is the standard derivation. You will get delta lambda is equal to lambda prime minus of lambda is equal to h divided by m e c 1 minus cos theta. Here theta is actually what? Is the angle, right, between the scattered photon, right? Where is theta? Theta is actually this angle. Theta is actually this angle, right? Is the angle between your incident photon as well as your scattered matter photon. Okay, so that is the value of theta. Now, what is this h by MEC? Is called as Compton wavelength. Lambda c is called as a Compton wavelength, and this is given by h dot by MEC, which is equal to 2.462 into 10 to the power minus 12 meter. Okay, so from these two sets, this is a very, very important equation. Okay, this tells you that lambda prime is not the same as lambda, because why? Lambda prime and is equal to del lambda, which is called as a lambda shift, is h by MEC 1 minus cos of theta. If lambda prime will have been equal to lambda, then this right hand side will have been equal to 0, but it's not equal to 0. It depends upon your angle theta, right? So that means there is a difference between your lambda prime scattered photon and your incident photon, between scattered photon here and incident photon, right? So now, if you look at your the first assignment, okay, the question is okay, I'll write the question. So now I think you got it. There are one main important equations, which is given by del lambda is equal to lambda prime minus of lambda h by MEC 1 minus cos of theta. H by MEC is in fact what is called as a Compton wavelength, which is given by this value. Okay, so derivation, it is there in the textbook. Okay, no need, I don't need to go into the detail of it, but I'll just give you the final result. So now, if you look at the first question from your assignment, question number 1, if I think you have the questions, I'll not write completely, but what happens is like X-ray of wavelength 0.24 nanometer are Compton scattered and the scattered beam is observed at 60 degree to the incident beam, right? So is given the Compton wavelength. The Compton wavelength is given to you. The Compton wavelength of the electron is 0.00243 nanometer. The question is find, what is the kinetic energy of the scattered electron in? What is the kinetic energy of the scattered electron in eV, that is unit. So that means it's the same problem which I have just discussed you. There is an incident ray, X-rays, which is Compton scatter, okay, which is Compton scatter, and the scattered beam is given at theta is equal to 60 degree to the incident beam. That means if you look at the solution, what happens? Given lambda is given, that is your incident wavelength is given to be 0.24 nanometer, correct? And theta is also given to be 60 degree. Okay, what you need to find out? Compton wavelength is also given to you of electron, that is h divided by MEC, which is equal to lambda c, is also given to you 0.00243 nanometer. Then what do you need to find out? Sorry, is it the scattered electron? I think it's not. I think not scattered electron. I think this is scattered photon. I think not scattered electron. I think it's scattered photon in EV, right? So now, how do I solve these questions? Okay, you use the formula delta lambda is equal to lambda prime minus of lambda is equal to h divided by MEC 1 minus cos theta. This is the formula that I have just given it to you. Now what happens is that your lambda prime, now because you have to find the scattered photon, right? Lambda prime is equal to lambda, you take this on the right hand side, plus h divided by MEC 1 minus cos of theta. Okay, so what happens that now lambda plus h by MEC is, you can write as lambda c, which is the Compton wavelength, and 1 minus cos theta. So lambda is given to you 0.24 nanometer. That means it's already in the question, it's already given to you 0.24 nanometer. And lambda c is also given to you 0.00243 nanometer, okay, into 1 minus cos of theta is given to be 60 degree. Okay, so everything here you can calculate here, cos of 60 degree, then lambda prime is equal to 0.2412 nanometer. What is interesting here is that this is lambda prime. Okay, what is interesting is that lambda prime is slightly greater than lambda. Lambda is 0.24 nanometer is given to you, right, from the question. Lambda, the incident beam has a wavelength of 0.24 nanometer, whereas the scattered beam has a wavelength of 0.2412 nanometer. That means you will see here that whatever the scattered photon has a higher wavelength, which in turn has slightly a lower energy. So the higher wavelength, the lower will be the energy. That means indirectly you see that whatever the scattered photon from your electron will have a slightly lower energy than your incident photon. So now if I want to calculate what is the kinetic energy, how it will be? Hc by lambda minus of Hc by lambda prime. Okay, so what happens, we get Hc, we can take common, get 1 by lambda minus of 1 by lambda prime. Okay, so Hc will be 6.6 into 10 to the power minus 34, and C is 3 into 10 to the power 8, and 1 by lambda. Lambda is given to you, it's already given to you from the question, and 1 by lambda prime, what happens is that the lambda prime 0.2412. Okay, and if you solve these problems, you will get 396 into 10 to power minus 20 joules. Okay, here you just remember to replace this nanometer into 10 to the power minus 9. Okay, remember here also into 10 to the power minus of 9. So if you just equate this equation, you will get this much amount of energy. This is the kinetic energy. Now what happens, but the question is asked in terms of electron volt. So remember that 1 electron volt is equal to 1.6 into 10 to the power minus of 19 joules. So 1 joule will be equal to 1 divided by 1.6 into 10 to the power minus of 19 electron volt. Okay, so if I want to convert this joule into electron volt, what I need to do, 396 into 10 to the power minus 20 divided by 1.6. I have to divide by 1.6 into 10 to the power minus of 19, because 1 joule is equal to this much electron volt. Now what do you get? You get 24.75 electron volt. So this is your kinetic energy. Okay, so what really interesting from this problem is that you quickly see that your lambda prime, what suppose if your incident photon is scattered on the is incident on the electron, and it's scattered at a certain angle, and the angle is given as 60 degree. So what happens that your lambda prime, that means the wavelength of your scattered photon or scattered beam, has a slightly higher wavelength than your incident wavelength beam lambda. Okay, and that means your energy of the scattered photon is slightly less than the energy of the incident photon. Okay, this is what here also, this is what if you look at this equation that we have just describes also, what happens is that your delta lambda is equal to lambda prime minus lambda, and is given to this equation. So I have just used the equation, the standard equation which we have obtained from the derivation of your Compton wavelength. Okay, now okay, so let me check maybe if I have some more questions here and there, one or two. Okay, so let me give you one more problems. Okay, before we move ahead. Okay, let me give you one more problems. Before we move ahead. So this is related to your Compton effect. The first question was related to your Compton effect. Now the next question, before I move, I want to also solve one problems related to your photoelectric effect. Okay, this is not there in the assignment, this is extra. Okay, this is not there in the assignment. Sir, when you submit assignment, is important to write questions or not? Yes, I think it's better to write the questions, because such that it's easy for the people who analyze your assignments. Okay, it's better you write it. Okay, it's better you write it. Now, okay, this is not there in the assignment. The question number 2, okay, but that what I'm going to do now is not there in the assignment. Okay, just as an extra. Okay, so what happens is that question is, when two ultraviolet beams of wavelength lambda 1 equal to 80 nanometer and lambda 2 equal to 110 nanometer falls on a this is lead surface. Okay, they produce photoelectrons. Photoelectrons means the electrons ejected from the surface after a beam incident on the surface. Okay, that is your photoelectric effect. Photoelectrons means the electrons ejected out. Photoelectrons with maximum energies 11.390 electron volt and 7.154 electron volt respectively. So what does it mean? You see here, lambda 1 has lower wavelength, that means the energy of your incident photons is higher, so it also produces a higher kinetic energy, isn't it? 11.390 compared to your lambda 2. Lambda 2 has higher wavelength, but that means your incident photon has a slightly lower energy. That means the kinetic energy of your photoelectrons will be smaller. Okay, so the first question is that is estimate the Planck constant value. Constant value. Okay, this I have taken from one of the textbook, that the reference which I have given to you. Okay, from one of them. Okay, so what happens is that solution, you use the photoelectric equation. Okay, kinetic energy K1 is equal to hc by lambda 1 minus of phi, which is the work function of your metals, right? That means I'll just rename it. Hc is equal to mu plus kinetic energy. So h, mu is equal to c divided by lambda equal to phi plus kinetic energy. So your kinetic energy is equal to hc by lambda minus of phi. Okay, I have taken from your photoelectric standard equation. Now what happens is that, what about K2? K1 is for the first beam. Okay, there are two beams here. Lambda 1 is equal to 80 nanometer, and the another beam is, or the another energy or another radiation of lambda 2 is 110 nanometer. So K2 is equal to hc by lambda 2 minus of phi. So if you subtract this one, okay, if you subtract this one, K1 minus of K2, right, that is the kinetic energy 1 minus the kinetic energy 2, what will happen? You can take hc by lambda 1 minus of phi minus hc by lambda 2. So minus and minus will go plus phi. Okay, this phi is the same because it's the same surface. This is a lead surface, so it's the same, right? So phi, the work function of the metal, will be the same. So this and this will get cancelled. So you will get hc, and in bracket you will get 1 by lambda 1 minus 1 by lambda 2, right? This is kinetic energy K1 minus of K2. So interestingly is that now what happens? H, right? You can easily calculate H, which will be equal now to what? K1 minus of K2, right? And then you can carry this one here. Then you will get what? Lambda 1 lambda 2 divided by lambda 1 minus of lambda 2, right? And then divided by C. I have just rearranged this equation so that I can extract H, right? So it's very easy now. You know kinetic energy K1. K1 is 11.390. Okay, I'll just replace here. K1 is equal to 11.390. K2 will be equal to 7.154. Okay, lambda 1 is also given to 80 nanometer, which is equal to 80 into 10 to the power minus 9 meter. Lambda 2 equal to 110 nanometer, which is equal to 110 into 10 to the power minus 9 meter. And this is in terms of electron volt. So if you want to convert this into joules, what will happen? It will have 11.390 into 1.6 into 10 to the power minus of 19 joules. Remember this. Okay, remember this, because 1 electron volt, is equal to 1.6 into 10 to the power minus of 19 joule. Okay, here also will be 7.154 into 1.6 into 10 to the power minus of 19 joule. Remember that when you solve the problems, it's better to arrange everything in terms of SI unit, that is joules, meter, okay, kg, and so on, so that you will not have any confusion later. Okay, so here also I have done the same thing. I have expressed in terms of electron volt, in terms of the SI unit joules, and lambda in nanometer I have expressed in terms of nanometer, 10 to the power minus 9 meter. Okay, then you can just replace this. K1 you know, K2 you know, lambda 1 you know, lambda 2 you know. C is the speed of light. C is equal to 3 into 10 to the power 8 meter per second. Then after that, after you replace it, you can solve H. You can replace in this equation. I will replace it at equation star. H is equal to approximately 6.62 into 10 to the power minus 34 joule second. Okay, so you can estimate the value of the Planck constant from the photoelectric equation, using the photoelectric equation. Now, The second questions, the second questions which I would like to no the, not the second question, the second question of the same. Okay, that means this is I will say this is part A and this is part B. So part B is calculate the work function. Okay, because it's not given here, right? And your question is not given, the work function is not given. So how do you calculate the work function? Simply your h mu, whichever you have written, is equal to the work function plus the kinetic energy, right? So your kinetic energy is equal to h mu, no, sorry, not kinetic energy, your work function phi will be h mu minus the kinetic energy, right? So h mu, if you take one of them, if you take hc by lambda 1, you have kinetic energy k1, or you can also find phi is equal to hc by lambda 2 minus of kinetic energy k2. So if you use lambda 1, then you also have to use k1. If you use lambda 2, then you have to use kinetic energy k2, but both of them should give the same value. Phi, if you use lambda 1, phi is equal to hc by lambda 1. Lambda 1 is given to you 80 nanometer into 10 to the power minus of 9 meter, minus k1. K1 is 11.390 electron volt. 11.390 electron is 1.6 into 10 to the power minus of 19, and you substitute what is the value of h. H, you know, 6.6 into 10 to the power minus 34. I can write it here. H equal to 6.6 into 10 to the power minus of 34, right? Into 10 to the power minus 34 joule second, and C is 3 into 10 to the power 8 meter per second, and you will get what? Phi, after substituting, you will get 6.627 into 10 to the power minus of 19 joule. Okay, this is a very simple problems. Okay, now usually the work function is not expressed in terms of joules. Why? Because this is very low, 10 to the power minus of 19 joule. Okay, we usually express in terms of your electron volt, because the energy is so small that joule is not really a suitable unit. It doesn't mean that it is wrong, it's correct, but usually the representation is expressed in terms of your electron volt. That means 6.627 into 10 to the power minus of 19 divided by 1.6 into 10 to the power minus of 19, right, electron volt. So automatically you get approximately 4.14 electron volt, right? So using this photoelectric effect, you can calculate what is the work function of the metals and of the materials, or you can also calculate what is the kinetic energy after you shine your material with your incident beam. You can also calculate what is the kinetic energy. You can calculate what is the wavelength. Okay, and from your Compton scattering, you can calculate how much is a scattered beam. Okay, what is the angle or what is the wavelength shift. Okay, just like we have discussed. But most importantly, from these two problems, the take-home message is you have to express the energy in terms of a quantized energy h mu. Okay, we at this point, all of the problems that we have solved here, we have solved using energy is equal to h mu, right? So this, we have not used anything other than that. Every energy I have expressed in terms of h mu. This is one of your quantum from your Planck's quantum theory, which says that your energy is in fact equal to h mu. Okay, that is where this is just the starting of your quantum mechanics. Okay, that is where quantum classical physics cannot explain your photoelectric effect, cannot explain your Compton effect. Because why? In classically, wave is considered separately and particle is separately. And if you use from your wave theory, which says that okay, that energy is always, or energy is a continuous, it's or you can say a radiation is a continuous of is a continuous energy spectrum, which is not possible. Okay, but quantum mechanics says that energy is always a quantized unit of h mu. Okay, that is where you are able to solve these problems. Okay, so that is this is one sections of your problems. Now after this, okay, after this, what else that is coming into the picture? We will go to the second thing, which is called atomic spectra. Okay, the next question of your assignment are related to your atomic spectrum. Okay, so for your atomic spectra, you can also follow this book's concept of modern physics. Okay, concept of modern physics, Arthur Beezer. Okay, I have given it to you in the initial like in the initial class itself. Okay, in this, so this is one of the good books, okay, to follow this atomic spectra and so on. Okay, so now, what is really important in this problem is that after you have after we have considered that there is also a quantized unit of energy. Okay, now we are moving to a quantization principle, which says that okay, energy can be expressed also in terms of a quantized unit of h mu. Now what happens is that okay, let us take an example. Let us take an example. Suppose you have, when an atom, okay, gas or vapor is excited, right? Excited means they gain energy by the passage of an electric current. Electric current through it. The emitted radiation after being dispersed by a suitable spectrometer, okay, concentrated at a number of discrete wavelength. Okay, what does this means? Okay, what does this statement means? Suppose if you have some atom, atom, gas or vapors, and then you excite it by the passage of electric current. That means what happens? That means your atoms get excited to a high energy, they gain energy. So now when they gain energy, what happens? The radiation that is emitted from that is concentrated as a number of discrete wavelength. That means you don't have a continuous wavelength spectrum, but you have a discrete wavelength. Why is it so? Okay, why is it so? That means, example, I can rather say H alpha. That means the wavelength that is emitted is given by 6563 Armstrong. Second thing is H beta is lambda is 4861 Armstrong. You see, it's not continuous, but it has a certain the values of the wavelength of the emitted radiation. That means what happens is that Balmer, okay, discovered an empirical formula to explain these phenomena, as mu is equal to 1 by lambda, wave number equal to RH 1 by 2 square minus of 1 by n square, where n is greater than 3, 4, 5 and so on. Okay, that means you cannot just get a continuous wavelength whatever you want, but there is a certain discrete wavelength which are allowed. Okay, that means wavelengths are not continuous. The emitted radiation has a certain wavelength given by, let's say, lambda 1, lambda 2, and each of this lambda has a certain dependence, or okay, has a certain discrete values. I would rather say a certain discrete values. Okay, this RH is in fact 1.097 into 10 to the power 7 meter inverse. Okay, so what I would love to do is that let's see at this problem. Okay, this is the observation. Remember, again, this is the observations. So how do we explain this? Okay, how do we explain this phenomenon? So we will try to explain using Bohr's postulates. Okay, what does Bohr says? Bohr says that an electron, okay, an electron is moving in a circular orbit. Okay, an electron is moving in a circular orbit because of what? Because of the Coulomb attraction. Suppose I would like, this is nucleus, it has a total charge Ze, Coulomb attraction between the electron and the nucleus. Okay, that is the first postulate. Second postulate is that he says that out of many possible orbits, okay, there are classically there are many infinite possible electrons that electron can move around the nucleus, right? But he says that only those orbits in which angular momentum L is equal to nh by 2 pi are allowed. Okay, this is also a quantized a quantization unit, right? Because there is an n here. N can take values only 1, 2, 3, and so on. That means only the value, or only the orbits in which the angular momentum is an integral multiple of nh by 2 pi are allowed. Okay. Third, so that means it's all quantization. Third, that means suppose if you have initial state of energy EI and the final state of energy EF, then the energy radiation emitted is h mu is equal to EI minus EF. Okay, this is Bohr's postulate. Bohr's postulate says that electron can move in a circular orbit because of the Coulomb attraction between your electron and the nucleus. Second, he says that okay, if there are infinite possible orbits, but only few are allowed in which an integral multiple of in which a momentum is an integral multiple of h by 2 pi are allowed. And third, he says that suppose there is energy level EI and energy level let's say EI and EF here, then whatever the transition of the electron, okay, whatever the transition of the electron, the energy h mu is equal to EI minus of EF. Example, I will give you an example. Suppose you have an electron. Suppose you have an electron going up to down. Down to up. Okay, from a lower energy state to higher energy state by gaining some energy. Let's say from your incident radiation or the incident beam and so on. Right. But now, when the electron comes back from the final state to the initial state, or your initial state to the final state, it releases h mu. Right? Whenever an electron or an atom release or goes from your excited state to your final state, it releases a photon of energy h mu, and this h mu is in fact equal to the energy of EI minus EF. Okay, that is why it always have a quantized unit. Now let's move ahead. From Bohr's model, what happens? Just now I told you that electron move in a circular orbit, okay, with a nucleus of Ze. And what is the energy? What makes the electron move in a circular orbit? Because of the Coulomb attraction between this electron and this nucleus Ze. So nucleus has a total charge Ze, right? Z is the atomic number and E is the charge. Okay, so what will happen? 1 by 4 pi epsilon, this is the Coulomb attraction, 1 by 4 pi epsilon Ze into E divided by R square, isn't it? Ze is due to nucleus and E is due to the electron, which will be equal to what? Which will be equal to mv square by R. Okay, that means mv square by R is the centripetal force. From here, you can easily calculate what is the velocity, what is the radius. What I'm more interested is at the energy EM. The energy of the orbit is given by minus of m z square e to the power 4 divided by a n square h square epsilon square. So this is very, very important because your energy En depends on the quantum numbers n, right? So that means it's always a quantized values. So from here, what happens? If you solve, En is equal to minus of m z square e to the power 4 divided by a n square h square epsilon square, right? So if you solve this value, this is equal to minus of 13.6 z square by n square. That means you substitute what is the value of 8, h epsilon naught, m is the mass of the electron, and charge. Okay, so what is epsilon naught? You put the value of epsilon naught is, I think, is 8.834 into 10 to the power minus 12, if I'm not wrong. Or yeah, let me check, then I will get it back to you. So epsilon naught. Okay, you substitute the value of epsilon naught, then you also substitute the value of mass, which is the mass of the electron. You substitute the charge E, then you can get this energy. Okay, now because of that, you have your energy, which is depending on your n square value. Okay, so we will go to the last section. Okay, after knowing the energy, then what happened? Frequency, this is energy En. Okay, that means you have energy E1, which is equal to minus of 13.6. Okay, let's say for an hydrogen atom, which is minus of 13.6 electron volt. Then if you have to find out what is the value of E2, then you have to substitute here. Instead of n square, you will have to substitute. Let me just write it here, that will be better. That will be better. So E1 will be equal to minus of 13.6, and then z square by 1 square. E2 will be minus of 13.6 z square by 2 square. And for hydrogen atom, z equal to 1. This is in terms of electron volt. Okay, that means this energy will be equal to minus of 3.39 electron volt, right? And E1 is simply minus of 13.6 electron volt. Okay, so now let's move to the second, which says that suppose frequency of electromagnetic radiation, EM is electromagnetic radiation emitted when electron jumps from initial orbit Ni to lower orbit Nf. Then what happened? Then frequency mu is equal to, I have told you, Ei minus of Ef divided by h. I have just told you just now that the energy E, which is the radiation emitted, right, due to the when the electron jump from a higher orbit to a lower orbit, is given as E is equal to Ei minus of Ef. Okay, I have used this formula. Now what happens? Mu is equal to energy. You can use this relation, okay, which is equal to minus of mz square e to the power 4 and so on. So there is another also. Let me just check. En, I'll put the formula on the right hand side, minus of mz square e to the power 4 divided by 8n square h square epsilon naught square. You can also express this equation, in terms of R infinity. R infinity is not infinity, we get m e to the power 4 divided by a epsilon naught square h cubed c. Okay, so that means your energy En you can also express in terms of minus of R z square h c by n square. Okay, that means you can also express the energy whatever you have given in terms of R infinity. That means now mu is equal to what? Mu, which is equal to Ei minus Ef, you can express here R infinity z square h c by, this h will come here, and 1 by nf square minus of 1 divided by ni square, right? Because n is coming from your equation En. Then mu, you can take c left, we can take some R z square, okay, 1 by nf square minus of 1 divided by ni square. Finally, you will get mu by c is in fact wave number. Mu bar is equal to R z square 1 by nf square minus of 1 divided by ni square. This is very, very important, because This is what it explains you, right? R infinity is equal to m e to the power 4 that we have just mentioned, 8 s naught square h cubed c, which is equal to 1.097 into 10 to the power 7. Okay, and this is exactly what you see in the like what Balmer, okay, what I have just shown you, that whenever there is an atoms, vapors get excited, and then when they emit radiation, okay, they emit at a certain fashion which follows exactly this formula, right? So that means you have now, what happens, you have a series called Lyman series. Lyman series means nf equal to 1, that is your final state, is the first state, and ni can be 2, 3, 4. Lyman Balmer, okay, then I will write it here, mu bar is equal to what, r infinity z square 1 by, since nf is equal to 1 square minus 1 divided by n square, and I will be 2, 3, 4, and so on. This is called as the Lyman series. That means, suppose um, if that electron jumped from any excited state to the first ground state, nf is equal to 1, then you have what we call as the Lyman series. Balmer is nf equal to 2, ni is equal to 3, 4, and so on. That means mu bar is equal to r infinity z square 1 by 2 square minus of 1 divided by ni square. Here ni starts from 3, not from 2, it starts from 3. Lyman, Balmer, and then Paschen, nf will be equal to 3, and ni will be equal to 4, 5, and so on. Okay, bracket, nf will be equal to 4, and ni will be equal to 5, and so on. And finally P1 series, nf equal to 5 and ni equal to 6, 7, 8, and so on, 5, 6, and so on. So these are called as a Lyman series, Balmer series, Paschen series, bracket, and P1 series. Why? It's because your final state, with what is fixed is that your final state. For Lyman, nf is equal to 1, for Balmer, nf is equal to 2, for Paschen, nf is equal to 3, bracket, nf is equal to 4, and P1 nf is equal to 5. Okay, so now we will solve the problems. Okay, that is the question number 2 of your assignments. Okay, question number 2 of assignment. But before we do that, I'll just introduce one more term, reduced mass. I'll just introduce this one, reduced mass. Suppose, okay, reduced mass mu, suppose if there are two masses or finite masses, you can represent small m, capital M divided by small m plus capital M. Okay, I will not derive this one, I'll just give you, because an energy now, instead of En is equal to minus of mz square e to the power 4 divided by 8n square h square s naught square, you can replace to be minus of mu m square, sorry, minus mu z square e to the power 4 divided by 8n square h square s naught square. Okay, so your energy is not simply m anymore, it will be instead of mu. Okay, and when there's a reduced mass, okay, reduced mass means if both mass are contributing. Okay, so we have to express in terms of mass, mu is equal to small m capital M to small m plus of capital M. Okay, and usually in your in your initial formula, we express En as minus of simply m, which is the mass of the electron, z square e to the power 4 divided by 8n square h square s naught square. But whenever we are talking about the reduced mass, we are talking about En, you have to, instead of the mass m, you have to replace by the reduced mass m. Okay, okay, so now let's solve the question number 2. Okay, let's solve question number 2. Yeah, so I think you have the question assignment number 2, so I don't need to to write it again. So what happens is that he says that a mu1 is a mu1 from cosmic rays is trapped by a proton. See, a mu1 from cosmic is trapped by a proton to form a hydrogen light, atom, right? To form a hydrogen light atom. Given is given to you, given the mu1 is approximate 200 times heavier than the electron. The longest wavelength, the question, the longest wavelength of the spectral line, the longest wavelength spectral line in analog of the Lyman series of such atom will be dash. Okay, fill in the blanks. So that means this is given to you. That means you have to find out what is the longest wavelength. Okay, the question is you have to find out the longest wavelength. What is the longest wavelength of the spectral line in Balmer's in the Lyman series? And quickly, you know now, Lyman series is, NF is equal to 1. That means the ground state, right? We are talking about the ground state now. Solution. But since I'm talking to you about a reduced mass, you see now there is a mu1 here, and also there is a proton here to form a hydrogen light atom. So you are talking about the reduced mass because there are two components here. So reduced mass mu equal to mass of the mu1 and mass of the proton divided by mass of the mu1 plus mass of the proton. I have just used the formula of your reduced mass. So now mass of the mu1 is given to you to be 200. The mass of the electron is given to you. Given the mu1 is approximately 200 times heavier than the electron. That means 200 mass of the electron plus. What is mass of the proton? Mass of the proton is in fact 1836 mass of the electron. So you can replace 1836 mass of the electron, and here also 200 mass of the electron into 1836 mass of your electron. Okay, if you solve this one, add this one and the multiplication, you get 180 ME. So this is your mu1, right? So now you know mu. So what we need to find out? We need to find out the longest wavelength. We need to find out the longest wavelength, and longest wavelength automatically it is related to your energy, right? So how do we calculate the wavelength? We can calculate first using the energy, then you can back calculate the wavelength. So what you need to do? You can calculate En, right? Is given to you. Is given to you minus of mu z square e to the power 4 divided by a n square h square epsilon square. This is the formula from your Bohr's postulates, correct? But instead of m, we are replacing it by reduced mass mu. So now what we can do is that we can also replace this one minus of mu. Okay, you can add mass of the electron here. Okay, you can mass of electron z square e to the power 4, and here also we can mass of electron such that the numerator and denominator will get cancelled, right? So we get a n square h square s naught square. So this term minus of m z square e to the power 4 8 n square h square s naught square is equal to what? Is given to you have already calculated to be equal to En of your hydrogen atom. Mass of electron z square e to the power 4 divided by 8 n square h square epsilon square is in fact energy given to you by En z square by n square. The term which is coming into the picture is mu divided by me. Right? The additional term is only mu by me. So in other words, I will also write mu divided by me. Okay, En divided by n square. Why I put z equal to 1? Right? Why I put z equal? Because it is a hydrogen atom. I can put z equal to 1. Now, so for ground state, because it's a Lyman series, for ground state, what happens? I can name here En prime. Sorry, I can name here En prime so that you can understand. En prime, that is V1 prime equal to mu by me. You have already calculated with 180 mass of the electron, so you can get 180. Okay, and this will be equal to E1 because your n is also equal to 1. So mu by me from here, mu by me equal to 180, right? So E1 prime is equal to 181 and E2 prime is equal to 45 E2. How do you get E2 prime? By just substituting here n to be equal to 2. It's the same thing. Okay, you use the same thing, mu by m is equal to 180 and this is E1 and this is and n square you substitute 1 and here in n square you have substitute with 2 for your first excited state. For the first excited state. Okay, now what happens? The question is find the longest wavelength. The longest wavelength in the Lyman series, right? The longest wavelength, it corresponds to, you remember, the lowest, or it is analogous to the lowest energy. The lowest energy means analogous to transition. I will write it, transition from first excited state to ground state. Right? Remember, there are possible, okay, there are possible transition also, like second excited state, third excited state, and so on. But here here the question is longest wavelength. Longest wavelength is obtained only when the energy or analogous energy is, the energy emitted will be very, very less. Energy emitted will be less means transition from your second state to the first excited state. I'm sorry, the transition from your first excited state to your ground state. If I have to draw slightly the just on the sides, if I have to draw, suppose this is your E1 and this is your E2, this is your E3 and this is your E4 and so on. So the longest wavelength will be transition from E2 to E1 because this has the lowest energy. This has higher energy, so the wavelength will be much lower. So the question is for the longest wavelength. So you have to find out what? Delta E equal to E2 prime minus of E1 prime. You substitute 180 into E1 minus of 45 into E2. Correct? And what is E1? You will get 180. E1 is minus of 13.6 electron volt, right? So sorry, so 45, this is sorry, here is not E1, it should be 45 E1. Okay, so what happens is that 45 E1, so you can get 135, and then E1 is minus of 13.6 electron volt. You will get something like 2937.6 into 10 to the power minus of 19 joules. Okay, so this is the energy that you are getting, and simply once you get the energy, then delta E is equal to hc by, you can calculate what is the longest wavelength. Lambda will be equal to hc by delta E, and hc we can 6.6 into 10 to the power minus 34, you can add, into c3 into 10 to the power 8 divided by delta E is 2937.6 into 10 to the power minus of 19. So if you solve this problem, both of them, we'll get 0.0067 into 10 to the power minus of 7 meter, which is equal to 6.7 Armstrong. Here Armstrong means 1 into 10 to the power minus of 10 meter. So it's usually expressed in terms of 10 to the power minus of 10 meter. Okay, so this is the second problems. Okay, this is what you can get from your second problems. Okay, from your second problems, the question is find the longest wavelength of the spectral line in the Lyman series. Okay, that means you have to find out the energy of the first excited minus the energy of the ground state, then you will be able to calculate your wavelength. Okay, now the third question, which is much more easier. Okay, the third question again is exactly similar to this. Okay, third and fourth questions are very similar to this. Okay, so I'll just solve again question number 3 of your assignments. Okay, now what happens is that The question is the photons from the Balmer series. Now remember, is the Balmer series, not the Lyman series. From the Balmer series in hydrogen spectrum, in hydrogen spectrum, having wavelength between 450 nanometer to 700 nanometer are incident on a metal surface. The metal surface of work function 2 electron volt. Find the maximum kinetic energy of ejected electron. Given Hc is already given to you, 1242 electron volt nanometer. Okay, so these problems, it relate between your Balmer series and also it relate between your Balmer series it relate your Balmer series as well as your kinetic energy of the ejected electrons. So what you need to do, you know that, right? For Balmer series, NF, the final state will be equal to 2, right? You know. So what happens that E is equal to 13.6 1 divided by 2 square minus 1 divided by n square, and this energy is equal to Hc by lambda equal to 13.6 1 by 2 square minus 1 by n square. Okay, this equation I have taken simply from here. E is equal to your minus of 13.6 z square by n square. Okay, I have taken from this equation. Then you can take 1 by nf minus 1 by ni. Okay, I have taken from here this relation. Now what did you do? I mean, how can you do? So now you need to find out the first one. The first one is because your final n is 2, so for the first one, for first excited, n is equal to 3, so you can take to be something like Hc is already given to you 1242 electron volt, so 1242 divided by lambda 3 equal to 13.6 electron volt. So this nanometer here, electron volt here, this is also electron volt, so 1 divided by 2 square will be 4 minus 1 divided by 9. Why? Because n is equal to 3, so n square equal to 9. Okay, so now what happens, lambda 3, this electron volt and this electron volt will get cancelled, lambda 3 will be equal to 6 5 7 nanometer. Similarly for n equal to 4, that is for the next higher state, 1 2 4, to use the same formula, divided by lambda 4, it will be equal to 13.6, we'll get 1 divided by 4, the same thing, because the final state state remain the same, which is equal to 2 minus 1 divided by, instead of n square 3 square, you will get 4 square, right? So you will get lambda 4 equal to 487 nanometer. Now if you look carefully, this is your lambda 4 and this is your lambda 3. So your lambda 3 and lambda 4 are within your given 450 to 700 nanometer. So that means a photon from the Balmer series, remember the photon from the Balmer series, that means having wavelength of 450 to 700 nanometer are incident on a metal surface. So now what you need to find out, you need to find out what is the kinetic energy. So the kinetic energy, using the formula of the photoelectric effect, h mu is equal to phi plus kinetic energy. So kinetic energy is equal to h mu minus a work function phi. H mu is equal to hc by lambda minus the work function phi. So hc is already given to you 1242 nanometer electron volt, right? And the lambda, which is the smallest, the lambda which is smallest, that means it will have higher kinetic energy, right? Find the maximum kinetic energy, that means 487. There are two things, lambda 3, which is lambda 3, which is given to be 657 nanometer, and lambda 4 is equal to 487 nanometer. That is what you calculate in the first section, right? Lambda 3 and lambda 4. But what happens at lambda 3, since it is the wavelength is higher, then it will have less kinetic energy, correct? But if your lambda 4, the incident photon has lower wavelength, then the kinetic energy also will be higher. Or in other words, you can say your lambda 4, since your incident photon has lower wavelength, it will have higher energy, and so the kinetic energy of the emitted electrons also will be proportional to your incident energy, or mu. Okay, so that's why you use 4H7. Why? Because you have to calculate what is the maximum kinetic energy. So minus phi is given to you, the work function is given to you to be work function is given to be 2 electron volt, 2 electron volt. So what happens? Minus 2 electron volt. So nanometer and nanometer will get cancelled here, so you will get 0.55 electron volt. Okay, so this is your maximum kinetic energy. So this third questions of your problems is done. Okay, now I have some 30 minutes, so I will solve the remaining 2 questions from your assignment. Okay, sorry. So I will solve the remaining 2 problems of your assignment. Okay, so in the next 20 to 30 minutes, so bear with me. Okay, so question number 4. Okay, so all of these problems in your assignments are related only to the atomic spectra. Okay, there is nothing different, you have to go beyond of that. Simply all are atomic spectra problems. Okay, so question number 4, the first line of the Balmer series, of hydrogen has a wavelength 6563 Armstrong. See, that means you have a transition, or you have a light or a radiation emitted with a wavelength 6563 Armstrong. Calculate the wavelength of second line. Okay, if I want to express in terms of your, in terms of graphical representation, visualization, let's say this is n is equal to what? 2. Remember that n is equal to 1 is for the Lyman series. Whenever the transition goes to n is equal to 1, is called as a Lyman series. Whenever any transition from any higher energy state goes to n is equal to 2, is called as the Balmer series, right? So this is n is equal to 3, n is equal to 4, n is equal to 3, n is equal to 4. So whatever is given here is what? First line. This transition gives a wavelength of lambda is equal to 6563 Armstrong. So what you need to find? Transition from n equal to 4 to n equal to 2. So this is your second line. Okay, that is your question. Now what do? We use your normal Bohr's postulates, okay, which says that 1 by lambda, or wave number 1 by lambda. Let's say the first number is equal to r, let's say of your hydrogen. So 1 by 2 square minus 1 by 3 square, right? Because the first line is coming from the transition from n is equal to 3. So if you substitute, RH will be equal to 1 divided by 4 minus of 1 divided by 9, which will be equal to 5 RH by 36. Okay, now what happens to the second line, which is the transition 1 by lambda 2, which is the transition from what? 1 by, instead 2 square will remain the same, because your final state remain the same for your Balmer series, minus 1 divided by, but instead of 3 here, it will be 4. See, n is equal to 4 is your second line transition to n equal to 2. So will be equal to 1 by 4 square. What is this equal to? This is equal to 3 RH by 16. Now how do you find out the second line? You can just divide it 1 by the other. So that means, suppose this is equation 2, this is equation 1. That means 2 divided by 1 or 1 divided by 2, you will get the same thing. So we'll get lambda 2 divided by lambda 1. That means your left hand side divided by the left hand side, which will be equal to 16 divided by 3 RH. That means I divide equation 2 by equation 1, okay, into 5 RH by 36. What will happen? RH and RH will get cancelled. Okay, you will get 20 by 27. So lambda 2 equal to 20 by 27 into lambda 1. Lambda 1 is already given to you in the questions. So we get 20 by 27 into lambda 1 is 6563 Armstrong, which is equal to 4861 Armstrong. You see your lambda 2, your lambda 1, whatever the transition from n equal to 3 to n equal to 2 give wavelength of 6563 Armstrong. But the transition from n equal to 4 to n equal to 2, which is the second line, is 4861 Armstrong. Second line means a particular radiation, or the radiation emitted with a particle and the wavelength of 4861. Okay, the transition from one state to another state which produce an electromagnetic radiation or produce a photon with a particular frequency or with a particular wavelength of 4861 Armstrong. Okay, now okay, so that is done. Okay, that is done. And the second part of your question is find the wavelength separation. Find the wavelength separation of the first member of the Balmer series due to 1H hydrogen and deuterium. So this is very important. Now you have to find out what is the wavelength separation between the first member of the Balmer series due to hydrogen and due to deuterium. Now remember, now what happens is that, so remember, now we have to find out the wavelength separation between the first member of the Balmer series due to hydrogen and due to deuterium, 1H2. So this is the difference between 1H and 2H. Okay, but first member means what? Transition from n equal to 3 to n equal to 2. Remember, Balmer series, the final state is fixed and is nf is equal to 2. So what happens now? Solution, you can write 1 by lambda, I can write hydrogen 1 here, okay, equal to r hydrogen 1 and 1 by 2 square minus of 1 by 3 square, which is the same thing. You will get the same thing as 1 by lambda hydrogen 1 equal to RH1, which is the same thing 5 by 36, which is the same thing as we already have solved. Now lambda of hydrogen 1, if you solve, you will get something like 36 divided by 5 RH1. Okay, now what is the difference for your deuterium? So the same thing, 1 divided by lambda of H2. Okay, you follow the same thing. Okay, you follow the same thing, but instead of Z here, sorry, instead of Z n is equal to 1, now instead of Z equal to 1, you have the Z equal to 2. So 1 by lambda H2 will be equal to sorry, just a second. Yeah, okay. So 1 by lambda of H2 will be equal to what? This is for the deuterium. So lambda of H2 will be equal to 36 divided by 5 R H2. This is the Rydberg constant. Okay, R is the same constant which I have introduced before. Rydberg constant R, which is equal to 1.097 into 10 to the power 7. Okay, meter inverse. Okay, this is the same R which you have, which you know from Bohr's theory. Okay, which we have introduced it there. But the only difference there here is that, you know, you cannot use this. You cannot use the value of R here. Simply R. Why? Is because this is a reduced mass also comes into the picture. H2. It's not simply one atom. It's simply two of them. Right? H2. That is why you cannot use simply this R infinity which we have talking about. We have to use the R reduced mass. So R reduced mass is given to be RH1 is equal to R infinity 1 plus small m divided by mass of the hydrogen, and RH2 will be equal to R1 plus small m divided by 2 mass of the hydrogen. Why? Because there are 2 hydrogen atoms. Okay, this is the only difference. Otherwise, it's the same thing. is instead of using R infinity, you cannot use because there is also a reduced mass coming into the picture. So that is why you have to introduce RH, which is given by this formula. RH1 is simply 1 plus m divided by mass of the hydrogen. RH2 is equal to R infinity 1 plus small m divided by 2 mass of the hydrogen, because there are two mass. Okay, these, if you want to know this this formula, okay, if you want to know this formula, you can go to this concept of modern physics I have just told you. Arthur Beezer is there, or you can also have this Raj Kumar atomic spectra is also there. Okay, in that textbook is also mentioned about this formula, the details of it. Now, then you know now what is simply the lambda is equal to what happens, lambda h1 minus of lambda h2, which is equal to 36 divided by 5 r infinity into m divided by 2 mass of the hydrogen. So if you solve all these problems, you will get something like 1.78 Armstrong. Okay, so this is your the wavelength difference. Why? That means what you need to do here is that delta lambda h1 you can just replace with this lambda of h1, and lambda of h2 you replace with this equation, and then you take common 36 by 5 of lambda, and then you substitute r infinity. R infinity and r infinity will be the same, right? So then you have 36 by 5 of r infinity, and you will get this negative value m divided 2 of m mass of hydrogen. And if you also substitute what is the m here is the same thing as the mass of the electron, and mass of the hydrogen is equal to 1836 m mass of the electron. So again, you can substitute and you will easily get 1.78 Armstrong. Okay, so anyway, the notes also I will upload in the drive, and you can check it there also. Now the last problems is slightly related to different concepts, which is called as a phase velocity and group velocity. Okay, so I'll just give you the formula. I don't have time to to go into the detail of it, but again I'll give you the reference for it. Concept of modern physics, Arthur Beezer. It is there. Okay, there is the topics of phase velocity and group velocity, in which you can write phase velocity is equal to omega by k, and group velocity is equal to d omega by dk. Okay, so the question from your assignment is pretty straightforward. It's just this is d omega. So this is d omega. It's pretty straightforward. The wavelength and the frequency in a waveguide are related by lambda equal to c root over of mu square minus of mu naught square. Okay, the question is what? Express phase velocity as Vp is equal to lambda mu, and group velocity as Vp to Vg equal to c square. Okay, so this is a pretty straightforward problems. We just need to express the relation between your wavelength as well as your frequency is already given, and you can just express what is your phase velocity as well as your group velocity. Okay, when I say group velocity means the velocity of a group of waves, not individual waves. Okay, there is a group of waves. Okay, like maybe 2 to 3 waves. Okay, they will have a common Nanda velocity, which is a group velocity, not the velocity of the individual wave. Each individual wave will have, let's say, a different there are, or will have a different own velocity or a slightly different velocity from each other. That is called as the phase velocity. Phase velocity means the velocity of a single wave. But when you put a wave all together, what happens is that they all travel with a common velocity called the group velocity. Okay, the group velocity is actually the velocity of a group of waves. Or maybe let me just draw a slightly schematic diagram. Maybe you can have an idea. Let me just check. I can just draw on the side, okay, quickly. So suppose you have one wave travel this way and another wave also travel, let's say, this way. Okay, so now what happens is that you add one wave and another wave, the resultant wave will be something like, okay, and so on. Oh, sorry. Okay, something like this. Okay, I'll just give you this. I just give you an example. That means that suppose if you have two waves, okay, one wave and the other waves, each wave will travel its own velocity, call its phase velocity. But when you put them together, they will travel with a resultant velocity called the group velocity. Okay, this is just a simple schematic diagram. Okay, you can go more into detail into like in the textbook. Okay, they have a proper schematic diagram or reference. Okay, so for our purpose now, we have to express why your phase velocity is equal to lambda mu, not lambda v, lambda mu. Okay, so to do that, what happens that omega is equal to 2 pi mu. You start from the from your frequency, which is equal to 2 pi mu. This is equal to 2 pi c by lambda, correct? Then you have 2 pi c lambda. You can put your equation, given equation, c by root over of mu square minus of mu naught square. So c and c will get cancelled, so you will get 2 pi and then mu square minus of mu naught square. So this is omega. So now how do you express again? Because you have to express omega is equal to velocity is equal to omega by k. So you can try to express this value mu in terms of k. So how can we do that? We can do that using this relation. C is equal to mu lambda. So all the equations, I'll just write it on the right, which equation which I've used. C is equal to mu lambda. C is equal to mu lambda is equal to 2 pi by k, right? So mu is equal to ck by 2 pi. So instead of mu, I will write 2 pi, and mu square will be equal to c square k square by 4 pi square minus of mu naught square. This is omega. Okay, so now you just need to there is also interestingly, you can also note down here, simply here you can also note down here, omega is equal to 2 pi mu, which is equal to 2 pi according to this equation, mu square minus of mu naught square, correct? So mu, you can equate this equation, we get mu is equal to mu square minus of mu naught square. You can just to get an idea of your mu, okay? Or your mu is equal to c square k square by 4 pi square minus of mu naught square. Now we will go to the next case. We get phase velocity is equal to omega by k. Omega you already know, 2 pi root over of c square k square by 4 pi square minus of mu naught square. You have to divide this equation by k. Okay, so what happens is that this equation is mu, right? This equation here is mu. So you can either do a long calculation. Okay, let me just write it, 2 pi. You can do a long calculation. So if you put 2k inside the square root, you will get c square by 4 pi square, right, minus of mu naught square by k square. If you put inside the square root, then again you will get 2 pi divided by you can take this 2 pi outside, so you'll get 2 pi, and you can also take c. You will get something like mu square minus of mu naught square by mu square. Again, I convert this one k back using this formula. K is equal to 2 pi mu divided by c. Okay, so everything in terms of mu square, so 2 pi and 2 pi will get like the cancel, then we get c square divided by uh, lambda mu, which is equal to lambda mu. Okay, so you can easily express your phase velocity in terms of your lambda and the mu. Okay, it's just rearranging your velocity, your phase velocity vp as well as your lambda as well as your lambda mu. Okay, so if I want to do the group velocity vg, which is equal to d omega by dk. Okay, but then what happens is that you have to differentiate. Okay, so omega is, what happens to omega, you have already got from here, omega is equal to 2 pi from here. Omega is this relation 2 pi root over c square k square, so omega is 2 pi root over of c square k square by 4 pi square and minus of mu naught square, correct, minus of mu naught square. This is omega, so you just need to differentiate this formula. So what happens is that Vg is equal to d by dk, so d by dk you have to differentiate this dk, so you will get 2 pi, if you differentiate with respect to k you get 2 and root over of c square k square by 4 pi square minus of mu naught square, and then into, you have to differentiate the first term, 2 c square k by 4 pi square, and this, since this term is constant, it will go to 0. So now what happens, 2 and 2 will get cancelled, right, and again 2 with 2 also will get cancelled, so and then you will get what, you will get c square k, pi and 1 of this will get cancelled, c square k will still remain, and this term anyway is already equal to mu, that you already know, 2 pi mu. How is this term equal to mu? From here you see mu is equal to c square k square by 4 pi square minus of mu naught square, so you get c square k square by 2 pi mu. Then what happens, you will get this is Vg, right? So now what happens, you substitute the value of k is equal to 2 pi by lambda, so you get 2 pi by lambda into c square, this is also 2 pi mu, so your 2 pi and 2 pi will get cancelled, so you will get c square by lambda mu, this is Vg, and lambda mu is equal to what, c square by lambda mu is from your first equation, lambda mu is equal to your phase velocity, so you will get phase velocity, in direct you will get Vg Vp equal to c square. Okay. So that solves your problems, both the problems. So phase velocity is equal to lambda into mu, phase velocity into the group velocity is equal to c square. Okay, so that is what we found out. Okay, so Vg into Vp is equal to c square, and your phase velocity, the first equation is Vp is equal to lambda mu, and second equation Vp Vg is equal to c square. Okay, so yeah, so let's stop here. Okay, so in this session we mainly look into your photoelectric effect, Compton effect, as well as atomic spectra, and we also solve all the problems of your assignment, all the 5 problems of your assignment. Okay, I will also upload all these notes on whatever I have solved. I'll upload it in the drive, and then you can check it there. Okay, and any questions if you have, also you can always send a mail, or okay, you can always send a mail, or you can always ask. Then if you have any questions which you would like to solve, also that also we can look into it. Okay, so thank you so much for attending the class. Okay, I will see you next week. Okay, thank you.